Namaste, welcome to this channel, Dr.ARM's Chemistry. Friends, last time we have seen the introductory part of the electronic spectra of coordination compounds, in which we have seen the basic ideas regarding the electronic spectrum, the spectrophotometer, and the interpretation of that spectra for coordination compounds on the basis of the bands, absorption bands observed in the spectrum. So in that case we have seen that there are some broad bands obtained in the spectrum and there are very small bands which are obtained in the spectrum. Out of these, the two broad bands are showing that the energy required for the absorption is higher, and the very small or spin forbidden band is very small band for spin forbidden transition is appearing at lower energy, that is towards the right side in the spectrum, and the higher energy band is appearing towards the left side of the spectrum. Then we are going to see today the ligand field transitions. So here it is important to note that electron-electron repulsions which are occurring during transition are splitting the ligand field transitions into components with different energies. So depending upon the position of the various orbitals in the metal ion during the or after the formation of a complex, their position determines how the transition is taking place between the available orbitals, and it results in the spin allowed or spin forbidden transitions. So the amount of energy required for each type of transition varies because of the magnitude of inter-electron repulsion during the transitions. So we expect, if we take the example of this chromium hexaqua or NH3, we are taking this, the ligand is NH3 6,3 plus. The nature of ligand also shows effect on the number of bands or strength of the energy. Means that the amount of energy required for absorption for carrying out the transitions. Here the ground state configuration, here if we see, this is the D3 configuration of the metal ion, and if we see the distribution of electrons like this, and this is T2G, and there are these EG orbitals. So there are only 3 electrons present here in this T2G state, T2G orbitals, and each T2G orbital is of same energy, but their orientation is different. Similarly, the 2 EG orbitals are also same in energy, but their orientation is different. So this is ground state. This is ground state before, that is excitation, and this is termed as or shown as T2G 3 EG 0. Then after excitation, that is absorption of energy, say that is about 25,000, so approximately at 25,000 per centimeter around. This is approximate value. Means it is more or less depending upon the type of electronic state. So after this we find that the energy, means we can consider that there are 3 electrons and every electron from this can move to this EG orbital, giving another configuration, that is T2G2 EG1. So out of 3, any electron is capable to absorb the amount of energy around this, and it can enter into higher energy EG orbital. So as a result of this, we can have 2 electrons in any of the 3 orbitals, and it moves into this higher energy orbital. Now, the distribution also varies like this. So here, spin multiplicity is 4, means there are total 3 electrons. So 3 electrons into 1/2 is 3/2. So total spin is 3, and when this is taken as, means spin multiplicity is equal to, so if we take this, it is given by 2 into 3/2 plus 1. So this gets cancelled. 3 into 4, 3 into 1 plus 3 plus 1 gives 4. So the spin multiplicity is here 4. So we can have the electronic states or spectrophotometric states having the spin multiplicity of 4. So in alternate way, the 2 electrons are here, and the 3rd electron may enter into each orbitals with opposite spin. But your spin multiplicity is changing. The configuration is same, that is T2G, 2EG1, but the spin state is different. That is why spin multiplicity is equal to 1/2 spin, means 1 total spin is 1, but there is again minus 1/2. So the net spin here is 1. So 2 into 1 plus 1 is equal to 3. So the spin multiplicity for this type of excited state is 3. So in this way, we can have the different electronic states observed here. Now here we know that. So this is now clear. Now another thing we have to remember is that, say this is dxy, this is dyz, and third is dzx orbital. So the orbitals, 3 orbitals are different. So from this we can see the excitation may take place. The excitation of electron may take place from dxy orbital to this dz2, dz2, or we can have another options, that is dxy can show the electron from dxy can also move to the dx2 minus 1. Again we can have another option, dyz can move its electron to dz2, or dxz can move electron from one state to excited state, that is dz2. So there are these variety types of options, means depending upon the availability of space in the orbital, the excitation may take place. we will see how the excitation is initiated, or we can imagine the excitation. So for this purpose, we will show this diagrammatically. Now we can show this using the cubic shape. So you can imagine this cube. So this is our cube, and in this cubic shape we can show the axis. So we can show the axis like this. So this is x-axis. Then y-axis is like this. So we can imagine this as a y-axis, and we can imagine the z-axis like this. This is z-axis. So here, first of all, we will see the electronic transition from dxy to dz2. So the electron from dxy orbital is excited to the dz2 orbital. So during this, we should imagine the position of orbitals. So this dxy orbital is oriented. So we can have this center of these all axis. Then the xy, the orbitals are present between the x-axis and y-axis. So here this is the x-axis part, and this is also y-axis. So these orbitals are lying between these axes. So we can imagine these orbitals like this. This is also another part of these orbitals. Now we will have another. So this is one loop, and it has another loop lying between these axes. So the x-axis and y-axis. Like this. So we can mark these. Say these are plus plus sign, these are having say minus minus signs. So electrons, so this is about only dxy orbit. Now we will show the other orbital having dz2 axis. So dz2 is shown in this way. So there is one part here. So this is about the dz2. Means we have shown only some part of this in order to avoid confusion. So there is also another part in circular form, but it is hid behind the lobes of dxy and dyz orbitals which are pointing towards us. Now if we see, we have to see that these electrons, say if we take this dx1, so electrons are present either in these or in these, or these are the lobes of the dxy orbit. So when this transition takes place, the electrons are moving from these dxy orbitals to this the electron is moving from these dxy orbitals to this dz2 orbital, like this. This either this or these two electrons are moving in this way. So the distance between this dxy and dz2 is larger as compared to the distance between these dxy and the x2 minus y2 orbitals which are lying in the same xy plane. So this transition shows more electron repulsion. Shows more electron repulsion. As a result, it takes place towards the higher energy side in the spectrum, as we have seen in the previous lecture. That is, it appears at about 25 approximate value. So it is 25. We have seen that the first transition is appearing at 28,500 per centimeter, and second transition is appearing at 21,500 per centimeter. So these are shown by the two bands, but for this type of dxy orbital, it contains the electron. So we have shown that. We can see that. See, these are the say this is dxy, and each orbital has this one electron. But if we consider, see, this electron is excited to the d Eg orbital. This is T2G. So this requires more energy because it is relatively at larger distance from the dxy orbitals, because dxy orbitals are lying in the xy plane, whereas the dz2 orbital is lying in the direction of z axis. Further, means why there is more electron repulsion? Because there are other orbitals here. So we know that. What are other orbitals? Say this is dzx and this is dyz. So this orbital is lying between z and x axis. See, this is x axis and this is z axis. So this is x axis and z axis. So these orbitals are lying between z and x axis, and the orbital already have electrons. These orbitals are already having electron, but these orbitals are lying relatively closer to the dz2 orbital. So you can imagine the z axis here. Dzx means the orbital is lying between the z axis and x axis. So the electron density is lying more. The electron density is more close to this z axis or around the z axis. Similarly, there is also one electron, and that dyz orbital is having lobes between y and z axis. So the electron density is more because of the two electrons near z orbital or dz2 orbital, that is in the direction of z axis. So there are more electron density already present, means before carrying out excitation. Before excitation of the electron, the dzx and dyz orbitals are already occupied, and because of this, the dz2 direction shows more electron density. These are electron rich. Our electron density is more and in the direction of z axis. So this electron density will show more electron repulsion when the electron is moving from this dxy orbital into this dz2 orbital. So if you see this is dz2 orbital. Then the electron repulsion. This electron when moves to dz2, it suffers strong repulsion because of these electron rich orbitals, which are lying closer to this dz2 orbital, and that is why it shows larger or broad band, and it is higher, as we have seen earlier in the spectrum, at around 28,500 per centimeter. First, larger band occurring at higher energy side in the spectrum. Then, so this is about dxy orbitals. Then we can have the other orbitals. So if we consider the orbitals like this. So we can have the orbitals, that is d, for example, dzx or dyz, we can consider any. Okay. So if we consider dzx, here we can have this axis. So this is the center. So if we imagine the So this is x, y and z. So we will have the orbitals, that is dzx. So dzx shows excitation to dz2 orbitals, or we can consider similarly dyz shows excitation to dz2. We can imagine any of that. So if we consider this dyz, we can imagine, or dzx we can take here. So if we take this x-axis here, the orbital is lying between these like this. So this is dzx. Similarly, dzx is also lying here. Like this. The lobe is like this. Then another lobe is having structure like this. Now we can consider these orbitals. So the green colored orbitals indicate the dzx orbital. So the opposite lobes are having say plus 1 or plus sign of wave function. These are having say minus sign of wave function. And there is dz2 orbital, which is having the like this. And there is another lobe which is ring form in the ring form. Now you can imagine that these orbitals are lying much closer . This is dz2, and these are the other orbitals are this. So we can show this, these orbitals, that is dzx. So here these two types of transitions are possible. So the electrons are moving from this dzx orbital, the zx orbital to this portion, and these orbitals to this portion. So in this way you will find that the dz2 and this dzx are like much closer. That is why the electron density, there is also already one electron in dx1, there is also one electron in yz. The dz2 is empty, but these electrons are having electron clouds. There are electron rich space. This is because of the closely spaced dzx or dyz with the dz2 orbit, and therefore the electron repulsion is relatively less. So here electron repulsion is much relatively less, and that is why it shows relatively weaker band. So it shows relatively weaker band compared to this type of transition, because it requires relatively smaller amount of energy. So as a result, it gives two distinct bands. So because of this, we have seen presence of appearance of two larger bands in the spectrum. Now, the spectroscopic terms are showing that, as we have explained, that these two transitions are spin allowed transitions, and therefore here the spin state or the symmetry nature of all these, each electron is characterized by T2G. So this electron has T2G, and T2G symmetry, and when T2G into this T2G into this third T2G gives A2G. That is symmetry, asymmetry or A2G symmetry. So in this way, the spin allowed transition is shown here. But we have seen that if the electron is moving in dz2 or any other this EG with opposite spin or reverse spin or -1/2 spin, then the energy required for absorption of such transition is very small, and it gives very small absorption band, and such type of transition is called a spin forbidden transitions. So only these two transitions are useful because they are using the same spin state, means the electron moves with the same speed. So this is +1/2. The electron entering here is also +1/2 spin. So it gives the D4, means quartet spin multiplicity. But if the electron comes here with opposite spin, the spin multiplicity is coming back to the 2, and such transition which is showing the change in multiplicity is not allowed. So it is forbidden. Means 4 transition, means 4 multiplicity changes to the doublet, means quartet is changed to doublet. So such transition is not allowed. It is called a spin forbidden transition. So this is about only the one part of this electronic spectra, that is ligand faded transitions. So we will see another part of this point in the next lecture. So see you next time. Please subscribe to this channel if not subscribed. Please press the like button as well as the bell icon, so that we will bring you the next episode, and that will be sent to you at the earliest. So thank you very much for watching this.